And then before we're integrating the area under this curve, y equal 1 over x plus 1, I drew part of it over here. The other piece would be down here. You see, we know this has a vertical asymptote at x equal minus 1. So that's what I drew it in over here, although that's not going to affect us because we're looking at the region below this curve and the line x equals 0 bounded by this curve, the line x equals 0, and x equal 2, let's say right here. And we're going to revolve, and y equals 0, which is the x-axis, and we're going to revolve about the x-axis. So here's our picture. Okay, so this is y equal 1 over x plus 1. So the volume is equal to the integral from 0 to 2 pi f of x squared dx. All right, so that's pi, the integral from 0 to 2, and this is 1 over 1 plus x squared. I'm going to write it as x plus 1 to the minus 2. Really, all we have to do here is the power rule. We can just add 1 to the exponent and get a minus 1 and divide by minus 1. So we can really treat this just like u to the minus 2. And that's only because that in this case the derivative of the inside is 1. So we can do our little linear u substitution, okay, but no constant's going to come out. All right, so I think I will do the u substitution anyway because that's what we're used to doing. So we would just write u equal x plus 1 and du is equal to dx. And then we have these limits to take care of as well, and so we'll do that. When x is equal to 0, if x equals 0, u equal 1, so I'll put that here. And if x is equal to 2, let me squeeze this in over here. If x is equal to 2, then u is equal to 3. So we're integrating 1 to 3, u to the minus 2, and dx is equal to du. All right, so that is add 1, and we have u to the minus 1 over minus 1, power rule, and pi and 1 to 3. So that is, substitute in 3, and we have minus 1/3. Substitute in 1, and we have minus 1. So we have minus 1/3 pi plus pi. So that comes out to 2/3 pi. In number 5, we're going to integrate a region about the line y equal 1. So first let's draw the region. Here's a picture of the region. This is y equal minus x squared plus 2. Y equal minus x squared is a parabola facing down through 0, 0, and we just lifted it up 2 units. Okay, to this point over here, this is 0, 2 on the y-axis. And we're looking at the region below y equal minus x squared plus 2 and above this line y equal 1, and we're revolving about the line y equal 1. So if we draw one of our little rectangles, it'll be sitting on the line y equal 1. Okay, and so basically we're going to use a similar formula to what we've been using in the other problems. All right, the volume is equal to, and these volumes are based on the formula pi r squared, which is the area of a circle. So this one as well, we have pi, and now for r squared, we're going to use the height of this disk, because the height of this rectangle, when this rectangle is spun around the line y equal 1, we get a disk, and the face of a disk is a circle, so that's why that's where the pi r squared area of a circle formula comes in. And then the dx, that's just the little width of or the thickness of the disk. But anyway, we're still basically using the formula pi r squared dx. All right, so where's the r here? Well, the r is going to be the height of a typical disk, so that would go from the line, the bottom of the height of a typical rectangle. The bottom of the rectangle is y equal 1, and the top is minus x squared plus 2. All right, so the height of this rectangle is the difference, minus x squared plus 2, subtract 1. Okay, this y height of minus x squared plus 2, subtract this y height of 1. So we have minus x squared plus 2, subtract 1. The general formula looks like this, and we're integrating from where they intersect. Okay, we're going to have to figure out those intersection points in a minute. Okay, so we'll fill these in a minute. The general formula looks like this. Okay, so we have the limits of integration, and then we have f of x minus c, assuming that we're rotating about this line y equals c. In our case, it's y equal 1 dx. That's the general formula. Okay, so we see we have to get these intersection points to know these limits of integration. So let's just figure those out. We're going to set this curve equal to this straight line to get the intersection points. So we're going to set minus x squared plus 2 equal to 1 because of the y equal 1. Y equal 1 and y equal minus x squared plus 2. So set this equal to this. All right, so just let's turn this around a little bit. This is x squared equal to, and then I'll subtract 1, x squared equal to 1. Plus minus square root both sides, so we have x equal plus or minus 1. So this is 1, this is minus 1, and this is 1. So we're integrating from minus 1 to 1. All right, so let's do that. Well, first we're going to square this out. I'll bring the pi out. And what are we squaring? We have minus x squared, and this is 2 minus 1 plus 1 squared. So we're just going to FOIL that out. Okay. All right, let me write it on top. Minus, we're multiplying minus x squared plus 1 times minus x squared plus 1. All right, just on the side, just to see what we're multiplying. All right, this times this is plus x to the 4th. Then we have these middle terms, a minus x squared and a minus x squared. That's minus 2x squared. And then we have 1 times 1 is plus 1. All right, let's integrate this. First term, x to the 5th over 5, use the power rule, minus 2x cubed over 3 plus x. And we're integrating from minus 1 to, we're evaluating from minus 1 to 1. Start substituting in. First 1, and we have pi, and here we have 1/5 minus 2/3 plus 1. Okay, minus pi. Again, just substitute in first minus 1, so we have minus 1/5. And then substitute in here into x cubed, and we're going to have plus 2/3 and minus 1. Basically, this is equal to this once we multiply through by that negative, because we do have symmetric region here. This and this are the same. So if we get a common denominator over here of 15, we end up with pi times 8 over 15, and over here again plus pi times 8 over 15. So we get pi times 16 over 15. In number 6, we're going to rotate this region, the region between square root of x and x squared, about the x-axis. So y equals square root of x and y equals x squared meet at the point 1, 1. So we're going to look at this region between 0 and 1, below y equals square root of x and above y equals x squared. Now here we drew one slice of the region, one rectangle, one slice. If we rotate this about the x-axis, since this rectangle doesn't sit on the x-axis, we're not going to form a disk. Basically, we're going to form a disk with a little hole in the middle. And we called this shape, we called this a washer. So we're going to use the washer method. Here's the basic formula for the washer method. And it's based on, it's again based on pi r squared, but here we're taking a large disk represented by pi r squared, uppercase R, and subtracting off the small little disk in the middle, represented by pi r squared with the lowercase r squared. So, so the big disk would be formed by this rectangle going all the way down to the x-axis. And the little disk is formed by this little piece underneath, that the part of the rectangle that is sort of missing, that doesn't touch the x-axis. And we subtract that out to get a washer shape, a disk with a hole in it. All right, so let's fill this in for our particular example. So we're going to integrate from 0 to 1. And the big R would be the rectangle from square root of R all the way down to the x-axis, or that would be the radius of the big rectangle. So that would be square root of x, or the upper curve. Little r is represented by the smaller curve by x squared. So let's just simplify this a little bit. So here we have x minus x to the fourth. All right, and we'll integrate using the power rule. And evaluate between 0 and 1. And we get pi 1/2 minus 1/5. All right, so we'll just put this over 10. And we have 3 pi over 10 for our volume.